Welcome to Applied Business Analytics. This is a short introduction to ridge regression. As its name might imply, ridge regression is just a different way of doing regression analysis on a set of data. And to understand the differences, let's go back to linear regression at the very beginning. We have a response variable y, we have an explanatory variable x, and typically we're going to have a lot of x's, but this is a very simple idea where we have y versus x. There appears to be a relationship between y and x, and the basic method of linear regression says fit align this data. Somehow, using some metric, fit align the data. That lets me do prediction and lets me explain how I think x is related to y. Now, it turns out there are many ways to fit align the data. Linear regression is the most popular way, but there are many, many ways to fit align the data. To understand how to fit align the data, though, we don't just do it arbitrarily. We want to have a reproducible method of fitting align the data. We have to put some notation here. We'll call our line y hat. So y hat is our line, and that is to make sure we understand the difference between y and y hat. So y are our observed values, and y hat, we might call those our predicted or our fitted values. And we'll call them predicted here. Now, what do we want to be true? We want the yi's to equal to yi hats. That'd be awesome. In general, that doesn't happen, though. Unless it's an exactly straight relationship, you're not going to have your yi's equal to yi hats. So remember, the yi's are your observed values. The y hats are your predicted values. We define what we call the residuals or the errors. We use the letter E, so you call them errors. So for each observation, there's an EI. And what it simply is the observed value minus the predicted value. And again, what would be awesome if all the EIs were to be 0, but that'd be only happening if you're fitting a straight line to a data set. That would only happen if it was a straight relationship. So again, for each x, there's going to be two values. There's the observed value for that x, and there's the predicted value of y for that x. And then EI is the difference. Sometimes EIs are positive. Sometimes EIs are negative. Over here, that's a negative EI. Sometimes EIs are actually close to 0. But the EIs are all over the place. Now, the EIs are very useful because they tell us how close our observations are to our predicted value. And so we use the EIs to figure out how to fit a good line to our data set because the EIs are the errors. So how do you fit a good line? There are many methods to fit a line to data. And that's what you want to be aware of. There are many ways to fit a line of data. Everyone has a different way of fitting a line of data. Some are more popular than others, but there are many ways of fitting a line of data. Now, when we say, what does it mean to fit a line to data? So back in high school or elementary school, you may have learned 2 points to find a line. Yeah, 2 points to find a line. But when we say fit a line, we mean find B0 and B1. So the equation of the line is y hat equals B0 plus B1x. And of course, B0 is the intercept, B1 is the slope. And the idea is that if I know B0, B1, I can draw the line. So B0, B1, define the line. Give me B0, B1, I know what the line looks like. I can draw it on the computer. So the method of least squares says find the line. And when we mean find the line, we mean find B0, B1. That makes the summation of EI squared as small as possible. We can't talk about the sum of the EIs because they're positive and they're negative. They might cancel each other out. So the method of least squares says find B0, B1 that minimizes. That's why it's called least squares. You're minimizing a square. So find B0, B1 that minimizes the sum of the residual squared. And that's actually a smooth function. You can take the first derivative, set equal to 0. You can actually analytically find B0 and B1 that does that. And that's the most popular way of fitting a line. It's built in Excel and R and every package under the sun. It's called the method of least squares. It's been studied for hundreds of years. Another way of fitting a line to data is called the method of least absolute deviation. And here, instead of squaring everything to make sure we're always dealing with positive numbers, we take the absolute value. So this is saying find the line that minimizes the absolute value of the EIs. It's called LAD for least absolute deviation. It is less susceptible to outliers in your data set. Because here you're squaring things. If you're an outlier, you're far away. You square it, you're even further. This is more robust, we would say. The math is a little trickier. Absolute values are harder to work with than squares. And so the math is a little more difficult. But it's another way of fitting a line to data. In tech speak, we call this the L2 norm, and we call this the L1. Sorry, don't mean to do that there. We call that the L2 norm, and we call this the L1 norm. So if you want to be really, really technical, you say, oh, I'm using L2 or I'm using L1, but it just means you're squaring things or taking the absolute values. But the point is, why stop here? There are many other ways to fit align the data, and that's just the main thing you want to understand is that when people come up with these new methods in data science, they're existing methods. They're just trying to find better methods out there. Well, what is ridge regression? Ridge regression says find the line. What does that mean? Find B0, B1 that minimizes this expression. So what is that? You want to minimize the sum of the EI squared plus lambda times B1 squared. You provide lambda. So I say, okay, let's use lambda of a certain value, and we want to minimize this. So this is the least squares part, and we're just adding on another component. It's just a different function. That's all it is. Different function. Computer doesn't care. Oh, computer has a routine built in to minimize things. You're just like, oh, you now want to minimize something different? Cool. I'll do that for you. So if lambda is 0, lambda is a positive number. If lambda were 0, it's least squares, right? Because if this were 0, it goes away. It's the same thing as before. And the idea is that it's a different line. The model becomes less sensitive to changes in the independent variable x as lambda gets bigger and bigger. It's kind of like this penalty term. And you can see you're trying to minimize this. You want to find the value b0 and b1 that minimizes that expression. And if lambda is really big, remember you want to minimize that expression. So if lambda is really big, 10, 20, 100, it's going to make b1 small naturally because it wants to minimize that. And that's all it's doing. But at the end of the day, what is it giving you? A different line. It's just giving you a different line. And why do you need a different line, right? Well, we got least squares. Why do we need a different line? Well, there are two reasons we do modeling, right? We're either trying to explain a phenomenon as is in front of us. We collected data, we're in sociology, or we're in a wet lab, or we're doing some science. It could be social science, but we're trying to explain a phenomenon. So we have some X's, and we want to explain some Y. Well, regression's fantastic. There's the idea of explaining what's going on in front of us. However, there's also the idea of using regression as a predictive model. We have a little bit of what we plan to see. Can we fit a model that relates X to Y that's going to be good for future values we haven't seen yet? Will our model generalize well? So the idea behind Ridge is it's not optimal for the data in front of us. Least squares is the best way to fit align the data. If you have one data set, you want to fit a line, least squares has many optimal properties. However, it may not generalize well. So the idea behind Ridge is let's have sort of a suboptimal line for the data set in front of us, which might perform better on future data sets. And that's all it's doing. It's giving you a slightly different line that you're hoping is going to generalize well to new data. Least squares also have some issues. When the x variables are correlated with one another, it's called multicollinearity. Least squares can break down. And also when the number of variables in your model, number of x is high relative to the rows of data, least squares also has issues. And Ridge shines, does a little bit better job there. So bottom line is Ridge produces a line that may generalize better to other unseen data. It's not optimal for the current data. If you just have one data set and you're trying to explain how the x's relate to the y, yeah, least squares is great. But Ridge may produce better predictions on new data, and that's why people like to use it. So summary, Ridge regression works by attempting to increase the bias to improve the variance. And also, okay, that is a typo, but I'm not going to go back and redo my 6 minutes of video right now. So we have what's called bias and variance. And there's a bias variance trade-off, and we have a short video on bias variance that you can watch also. And least squares is unbiased, Ridge is biased, but the idea is if you introduce a little bit of bias into your modeling, you might get lower variance and you might be better on future data sets you haven't seen yet. How does this work? This works by changing the slope of the line. You're minimizing a different function, you're getting a different line, but ideally that line will generalize better than the least squares line. The model performance might be a little poor on a training set. That is, least squares is going to beat on the training set, but it should perform consistently well on both the training and testing data sets. Here's an example And I know you're saying, what kind of example is this? You haven't really told us what the data is. There's no R code here. There's just some plots of lines on a data set. There's going to be a future video where we go through Ridge and Lasso and show you exactly how to do this in R. And it shines when we start looking at out of sample prediction, when we see how it does on a test data set. Here, just want to visualize this. Just want to impress upon you, you're just fitting a different line of data. So here we have a Y versus X relationship, and it's a little bit, maybe hard to tell here, it's a little bit curved linear. If you see over here, it starts to go down, flatten off a little bit. And what do we have here? This blue line is the least squares line. This is lambda equal 0.5, this is lambda equal 2, and this is lambda equal 10. And what do you see? You see different lines. Different values of lambda give you different lines. Lambda equals 0 is the same as least squares. That gives you the least squares line. And you're getting different lines. As lambda increases, the model becomes less sensitive to the variations of the independent variable. What do we mean by that? The slope gets closer and closer to 0. Remember how this works. Y hat is b0 plus b1 times x. A change in x is reflected in a change in y by b1. If x changes by 1 unit, y changes by b1. So as b1 gets smaller and smaller, a unit change in x has a smaller and smaller effect on y. Right? If b1 were 0, there'd be no effect. X changes and y doesn't change at all. And we see, interestingly enough, as lambda gets larger and larger, b1 wants to get smaller and smaller. It can't exactly get to 0 the way this works, but it's going to get smaller and smaller. So as lambda increases, the model becomes less sensitive to the variations of the independent variable. And that's what we're seeing here. So how do you pick an optimal lambda? Here we just throw in 3 different values of lambda. There's something called cross-validation you can use that finds an optimal value of lambda. You can try yourself different values of lambda and see which ones minimizes prediction error, sums of squares, and residuals, things like that. But essentially, cross-validation is a way you would first pick an optimal value of lambda, and then you'd use that line. But you can see as lambda increases, you get different lines here. So when do you use this? Ridge is particularly useful when the sample size is low, the x's are correlated, or the number of features is high relative to the number of observations. But it shouldn't be a scary idea. All it is a different line.